The instantaneous current and the phase relation between current and voltage of an LCR circuit can be determined using two methods, namely the phasor diagram solution and the analytical solution. In this module, we shall study the phasor diagram solution. Consider a circuit comprising of a resistor of resistance R, a capacitor of capacitance C, and an inductor of inductance L connected in series to an AC source with voltage V equal to Vm sin omega t. Here, Vm is the maximum applied AC voltage and omega is its angular frequency. As per the convention being used, subscript m denotes maximum value or amplitude of the quantity being considered. In the circuit, we see that the applied AC voltage V is the instantaneous voltage across the circuit. At any instant, the charge on the capacitor is Q. The current in the circuit is I, and di by dt represents the rate of change of current in the circuit. Instantaneous voltage across the capacitor is equal to Q by C. The voltage across the resistor is IR, and the induced EMF across the inductor is minus LdI by dt. The negative sign here denotes the direction of the induced current through the conductor according to Lenz's law. Applying Kirchoff's loop rule to this circuit, we get Q by C plus IR plus LdI by dt minus V equal to 0. Let this be equation 1. Since V is equal to Vm sin omega t, we get Q by C plus IR plus LdI by dt is equal to Vm sin omega t. As we know that the three circuit elements are in series, thus the current I through them is the same. Thus, we have I is equal to Im sin omega t plus phi, where Im is the amplitude of the AC current in the circuit, omega is the angular frequency, and phi is the phase difference. Now we will use the phasor approach to find the expression for the instantaneous current I. Let the instantaneous voltages or potential differences across the three circuit components be VL for the inductor, VR for the resistor, and VC for the capacitor. We know that the voltage in the inductor leads the current in the circuit in phase by pi by 2 in a pure inductive circuit. The phasor diagram for the inductor shows the phase relation between V and I in the inductor. Conversely, the voltage in the capacitor lags the current in the circuit in phase by pi by 2 in a purely capacitive circuit. The phasor diagram for the capacitor shows the phase relation between V and I in the capacitor. The amplitude of the voltage across the resistor is Vrm equal to Im into R. The amplitude of the voltage across the inductor is Vlm equal to Im into XL, where XL is the inductive reactance of the inductor. We know that XL is equal to omega L. The amplitude of the voltage across the capacitor is Vcm equal to Im into Xc, where Xc is the capacitive reactance of the capacitor. We know that Xc is equal to 1 by omega c. The instantaneous total voltage V in the circuit is equal to the algebraic sum of the instantaneous potential differences across the resistor, capacitor, and inductor represented as VL, VC, and VR respectively. And this can be vectorially represented as sum of the phasors VL, VC, and VR, which can be calculated as follows. The amplitudes of the potentials across the capacitor and inductor are VC and VLM respectively, and are at a phase difference of pi/2 from that across the resistor, that is VRM, and they lie on the same line on the phasor diagram. Hence, the phasors VL and VC lie on a line perpendicular to VR, but in directions opposite to each other. Considering the directions of VC and VL on the phasor diagram, we can obtain a single phasor for VC plus VL with the magnitude of VCM minus VLM. Here, we assume that the capacitive reactance XC is greater than the inductive reactance XL, and hence we have VCM greater than VLM. The phasor with the magnitude VCM minus VLM is at right angles to the phasor with the magnitude VRM. The amplitude of applied AC voltage, Vm, can be calculated by using Pythagorean theorem on the simplified phasor diagram. Substituting the values, we see that Vm square is equal to Vrm square plus Vcm minus VLM square. Using the values of Vrm, Vcm, and VLM, we get Vm square is equal to Imr square plus Imxc minus Imxl square. Vm square is equal to Im square into R square plus Xc minus XL square. Let this be equation 2. Or we have Vm equal to Im into under root R square plus Xc minus XL square. Now, we have Im equal to Vm by under root R square plus Xc minus XL square, which is equal to Vm by Z. Let this be equation 3. Here, Z is the impedance of the LCR series AC circuit, which is analogous to resistance in a DC circuit, and is equal to under root R square plus Xc minus XL square. Let this be equation 4. The impedance equation can also be written as Z square is equal to R square plus Xc minus XL square. This equation represents a right-angled triangle as per Pythagoras theorem. This triangle is called the impedance diagram. In an LCR series AC circuit, the phase difference phi existing between the voltage and the current can be determined by using the impedance diagram. In the impedance diagram, the hypotenuse gives the impedance Z. Here, we observe that tan phi is equal to Xc minus XL by R. Let this be equation 5. Phase difference phi is equal to tan inverse of Xc minus XL by R. Thus, the current flowing through the LCR series AC circuit can be given as I equal to Im sin omega t plus phi, where Im is given by equation 3, and the phase difference phi can be calculated from the equation 5. Hence, we have obtained information of all the entities we desired using the phasor approach to the LCR circuit.